This one's an initial value problem. We have the quantity of e to the x plus y times dx plus the quantity of 2 plus x plus y e to the y dy is equal to 0 with the initial condition y of 0 is equal to 1. Using the initial condition, we're going to be able to find the value of c that we keep putting on the right-hand side of the equation. And in this case, what I'm going to do is I'm going to solve the exact equation using a slightly different path, just so you have some variety and you can pick among the options that I'm giving you. First, we got to check to see if this is exact. And quick partial derivatives tell us that my is 1 and x is 1. So yep, it's exact. Now, we know that f of xy is equal to the integral of m dx. This isn't different from before yet. And so we have here e to the x plus y times dx is going to give us e to the x plus xy plus some function of y. This is where I'm going to depart from the previous strategies I've been using. It's also true that f of xy is equal to the integral of n with respect to y. In this case, that means it's the integral of 2 plus x plus y e to the y times dy. Now integrating this means we have y e to the y, which means integration by parts, and we would have that at some point using the other process anyway. It's all the same work, it just shows up in different ways at different times. Now for that integration by parts, I would say u is equal to y, so that du is equal to dy, and dv is e to the y dy, so that v is e to the y. And then, putting that together, we get f of x is equal to 2y plus xy plus, now from the integration by parts, y e to the y minus e to the y plus a constant of integration, but the constant is constant with respect to y. So it could be some function of x. Now what we have is one expression for f of xy that we found by integrating m with respect to x. And then another one, this should be f of xy. And then another expression that we got by integrating n with respect to y. Well, since we're looking for the same function both times, there's only one f of xy, we should have that e to the x plus xy plus h of y is equal to 2y plus xy plus y e to the y minus e to the y plus g of x. Now I'm going to do some color coding. We have xy on both sides. On the right hand side, the terms that have only y in them are 2y plus y e to the y minus e to the y. So that must be h of y that we didn't find when we integrated with respect to x, right? That's our constant function with respect to x. Then on the left-hand side, the term that has only x is e to the x. So that must be the g of x that we didn't get when we integrated with respect to y. Ultimately, f of xy has all the terms that we see in both of these integration results, but we don't repeat any of the terms that may happen to show up in both of them, right? We just need to supplement, in each case, whatever's missing. We'll find that f of xy in this case is equal to, I'm going to use this process at this point here, gathering things together. E to the x plus xy from when we integrated with respect to x. And then I'm not going to double count the xy, but when we integrated with respect to y, we picked up a 2y and a y e to the y minus e to the y. Now the form of solution that we're looking for does not have fxy equals, it is equal to c. If you didn't like this process, I don't blame you. There's a diagram in a previous process that you saw before. I'd say work it again using that technique. Go back to the previous ones, work it using this technique, see what you like better. Here we had an initial condition though, y of 0 is equal to 1. Remember that when we see that y of 0 is equal to 1, that means when x is 0, y is 1. Substituting that into the equation, you can verify that we end up with c equals 3. Therefore, our solution is e to the x plus xy plus 2y plus y e to the y minus e to the y is equal to 3. Next up, we have an equation that actually turns out it's not exact, but we are told to use an appropriate integrating factor. We'll get to that, but let's go ahead and see that this is not exact. We have cosine of x dx plus the quantity of 1 plus 2 over y times the sine of x dy is equal to 0. The partial of m with respect to y is equal to 0 because there are no y terms in m. The partial of n with respect to x, we can clearly see it's not 0, but I'm going to go ahead and write it down. It's 1 plus 2 over y times the cosine of x, and that is not exact. So we're going to use an integrating factor. We've got two options for an integrating factor, or rather two possibilities. The integrating factor is either mu, a function of x, which is e to the integral of the partial of m with respect to y minus the partial of n with respect to x over n times dx, or we have mu, which is a function of y, and it's e to the integral of the partial of n with respect to x minus the partial of m with respect to y divided by m times dy. Now these are the same nx and my that we use to find out if an equation is exact, so we didn't waste the work up there. At this point, you may have, say, two questions. One of them is, where do these integrating factors come from? I'll include that in the next video, which I'm going to call optional. The other would be, how do I know whether it's mu is a function of x or mu is a function of y? The answer is, if we find my minus nx divided by n, and that whole thing turns out only to contain x's, it's a function of x, then we have mu as a function of x. If we have nx minus my divided by m, and that entire expression only contains y's, I guess, or constants, but if it's only a function of y, then we have mu, which is a function of y. Sometimes they both will work. You could take your pick. Sometimes one turns out to work and one doesn't work. You just have to form one of these and see if it works. And if it doesn't, you form the other one. If it doesn't work at that point, then we're barking up the wrong tree, and this isn't our technique. Once we have the integrating factor, we multiply the equation by the integrating factor, and the equation mu times m dx plus mu times n dy, using whichever one worked, equals 0 is an exact equation. Now, in a moment, I'm going to ask you to pause this video and just go ahead and do the work. You have what you need in front of you and in the techniques in this video and the previous videos. I'm going to tell you, in this case, both mu of x and mu of y are going to work. You could do it either way. But I'm going to ask so that when you come back and you can compare your work with what I'm going to do, go ahead and find mu of x. Use that as your integrating factor, solve it, and we'll compare notes. Let's see how we did. When I formed my minus nx over n, we have 0 minus nx in the numerator, so negative 1 plus 2 over y cosine x in the numerator. And then n was already 1 plus 2 over y sine x. That goes in the denominator. The y's divide out. Actually, the entire parenthetic expressions divide out, leaving us with negative cotangent of x, a function only of x. Therefore, that can go into an integral that we integrate with respect to x. That as an exponent on e is a function of x, right? So that's how that all works. The integral of the negative cotangent of x dx is the negative of the natural log of the sine of x. And I went ahead and took that negative in front of the natural log, made it an exponent on sine of x, and so the result is the cosecant of x. When we use integrating factors, we don't use a constant of integration, and then any pluses or minuses that are getting dealt with from the e to the natural log of the absolute value, apply to both sides of the equation, we can drop them. We've seen that a few times already. Multiplying both sides of the original equation by our mu, which is cosecant of x, after simplifying, results in cotangent of x dx plus the quantity of 1 plus 2 over y dy is equal to 0. I went ahead and used the second technique that I showed you. It's a little bit cleaner this time. F of xy is equal to the integral of mu m dx, and so the integral of the cotangent of x dx. And that's going to be natural log of the absolute value of the sine of x plus some function that's a function of y, so it's a constant with respect to x, right? F of xy is also the integral of mu n with respect to y. And so we have the integral of 1 plus 2 over y with respect to y, and we see that that's y plus 2 times the natural log absolute value of y plus some function of x. For my final solution, f of xy equals c, I'm just going to gather all of the terms that I see in either of these integrals. Natural log of the absolute value of sine of x plus y times the natural log of, I again took the 2 in front of the natural log of y, made it an exponent. That actually has the added bonus of not having to write down the absolute values. Because we're presenting a solution and we have a natural log in it, the sine of x does need to be in an absolute value. We don't need to worry about it when it's e to the natural log of something and we're using that as some integrating factor. Everything washes out in that case. But when we have a solution that integrates to a natural log, that gets the absolute value. I know, kind of tricky there.